Hi from Ukraine, I am Alex, and welcome to my IBM Machine Learning Capstone project. The task in this project was to demonstrate the data processing and model development skills by using one of the technologies demonstrated in the IBM Neural Networks Capstone lecture course. Within the scope of this presentation, I'm going to demonstrate how I defined a problem and obtained input data, how I chose to prepare the input features from it, and to demonstrate the neural network development and deployment that would try to extract actionable insights from the input data. Now, for my problem, I really wanted to work on analyzing real-time data series, since they occur all the time in my field of work, which is structural engineering, especially in the context of unsupervised learning. So I decided to build an autoencoder type unsupervised learning network that would, once trained on historical data, extract anomalies or outliers from a real-time source. And I will demonstrate that on a historical Bitcoin price time series. So let's begin. Okay, so after some search, I decided to use the dataset of 1 minute time series of Bitcoin prices from a source on kaggle.com that spans a time frame from 2014 to 2019 on Coinbase online exchange. It is in CSV format and it has a permissive Creative Commons license. Now, as you can see, in some segments the data is quite sparse. It has non-valid values because there were no trades made during that time frame. So it's obviously going to require some pre-processing before we can use it. It has for each data point it has timestamp. It has open, high, low, and close prices, and it has general volume of trades during that time frame. So let's load it into our data exploration notebook and see what we can do with it. Here, as you see, I have already loaded the CSV source from IBM Cloud Storage source to a Pandas data frame in a Cloud Notebook. And let's see what it looks like. Now it looks exactly like in the source, and we are going to use a small subset of the data, one from the early stage and one from the late stage, to do some data exploration. Now, this is how data looks in the early stages. It has this gap that we saw earlier. So let's see what we can do on this slice of 5,000 data points. One way to fill the missing values, which are for this example like most values in the source, one way is to just fill the missing values with the closest previous valid value, which can be done via this expression in Python. And another way is to just drop the values by masking the not a number values. And since there are no missing values for the late stages of the time series, as you see, we don't have any dropped out values. I'm going to use the first way and just fill the missing values with the previous valid one. So let's see what we can do in the extract transform load phase. So let's do extract transform load. We have, as you see, normalized our data, and now we need to extract features array, proper features array to be used by our neural network-based autoencoder. And we need to select hyperparameters like length of a single sample, the training segment, which we're going to use to train our network, and the actual features to train on. Now we have the whole data set of around 2 million data points. And this handy function is going to extract a subset for training and extract features. And these are the hyperparameters I use. I have already tried time steps of 20 and time steps of 100, and they were given basically more or less random results on training. So by iteration, I arrived to the value of 50. This is 50 time steps in each window in each frame that we're going to feed to the neural network. And we use a small subset of our timeline to train the network on. And we are going to use just the two features, a rather simple combination. I have previously tried several combinations like opening price, closing price, and volume, and they were given bad results, so I arrived at this rather simple combination of just two columns per data point. So let's see what our feature array looks like. It's basically a NumPy array of the length of roughly 100,000, and its shape is two features per each data point. Now I'm going to define some handy helper functions. One is to scale the feature array. One is to transform the continuous data frame to separate input arrays by the length of time steps, and another one is to transform it back. So now we have a scaled feature array, and we're going to save the number of dimensions, which is our number of features, as this variable dims. Finally, with data processing out of the way, we are now getting to the proper model design and training. Here we have some helper functions that are going to show our loss, and we are using Keras high-level modeling framework and TensorFlow backend with Keras. And this is going to be our builder function for model, which assembles model from the number of layers, number of nodes in each layers, the hyperparameter of time steps, and the number of features in each point of time of our input data set, the number of dimensions, number of features. And we're going to use a sequential model. Now, I tested several neural network designs for this project, and the first was a classic autoencoder with an input and output layers of dimensionality of 50 by the number of our time steps, and a hidden layer with 3 to 5 nodes. And unfortunately, it proved to yield mostly random results after training. So after reviewing some newer sources, including by Romero Kinsler, I arrived at this design mentioned by him, which is a long, shorter, an LSTM network with a number of layers of 11 and 50 nodes in each layer. So we're going to build this sort of neural network architecture. And we're going to add the output layer, which has dimensionality of our number of features, and we're going to compile the model. Now these are our helper functions for model training, and we have the default amount of epochs to be equal to 20, and we're using the batch size of 72. We also have a helper function that allows us to score model on new data sets. And after training, we're going to deploy the trained model. We are going to detect outliers in our real-time data frames, our actual working data frames, by evaluating these data frames on the trained model. We have a helper function to prepare a single set of 50 time steps. And just to remind that our scaled array has a dimensionality of roughly 100,000 data points and 2 dimensions. And now we can arrive at actually training our model on our prepared dataset. And I'm going to go for 2 takes in training the models, and this can be considered basically as another hyperparameter in model training, because the more takes we make on training, the less outliers the model is going to detect due to its architecture, and this can be tuned to either have more frequent signals about an anomaly in your real-time data, or you can have more takes, which will result in less signals being generated. And I'm just going to go with 2 here. So we're looking at the loss function here, and we now have to wait for about an hour for the model to train, and then we are going to try to deploy it. Okay, so now that we have trained our model, right here, we need to deploy it to production. And what it means to deploy a model, it is to provide a service that can be accessed from some another tool that you use for your actual work, to be able to feed the real-time data frames to the model, and to be able to get the loss function. And the loss function will be our actual output feature here. Small values in loss function will detect sort of a normal data frame, and higher loss function will mean that this data frame that we are currently feeding from our real-time source is an outlier. Now I want to show you the functions that I use to save model into the GDFS format with the extension H5, and I'm going also to save the test slices to a JSON format that I'm going to later use in another notebook as a simulation of a real-time data source. These frames are taken from another slice of our raw data that we have got previously. Now, for the deployment, I chose the serverless framework, and it's actually a fun part of the project. I'm now using the serverless framework to deploy a Lambda function to a Google Cloud platform, which is a completely different service from where we trained our model. And this specification shows that we are going to use the Google Cloud functions, and we are going to use our model, our deployed model that we are going to put into the Google Cloud function. And we are going to use this code to actually output the result on the trained model. We are using the same parameters to be able to slice our time steps and so on. Now the process of deployment has already been finished, and I'm going to use another notebook to show you how to actually query the model. So here we have the deployment notebook, which is a completely separate notebook. It doesn't know anything about our model, so we are just going to load our test slices, which we have already put into cloud storage in this asset, in this project, and we are going to get the time slices from the JSON strings that we store in our test file. Then we are going to import our NumPy array and look at its shape. And we have, as you have just seen, we have 419 separate time slices that we are going to feed to our model. Here the process has already started, as you see, and we will be able shortly to chart our data and see if we have any outliers in this particular data. Okay, so now the process of processing our test data has been finished, and what's actually going on here? We have deployed the model to this cloud function, which is publicly available, since the issues of security are not in scope of this project, and we are doing simple post requests over the network to this endpoint. And in the losses array, we have 419 losses per each data frame, and now we're going to try to output the losses. And as you see here, after the process of unsupervised training of the model, we have about 2 clear outliers on our test dataset, and we are going to try to chart to look into these outliers and to see what kind of data they carry. I am manually defining the maximum loss that I consider to be an outlier. This is just part of the black magic of machine learning, since we have kind of this cutoff for the outliers that we have in our current test set, and we can probably try to either predict it or to take some sort of average values over the whole loss function over time. And we have these neat test data frames as outliers. And we can kind of see that the neural network was able to identify these characteristic dips, and it considers these time forms as outlier functions, and we can continue working with the model to try to make use of this data to turn it into actual actionable insight. So this is basically the result of the project. I hope you enjoyed it. Thank you.